Hello everyone, my name is Jin Yang. I'm a PhD student at the Record Artificial Intelligence Lab, University of Campinas. My advisor is Professor Anderson Rocha. I'm here to present our paper, Scalable Fact-Checking with Human in the Loop. Our motivation for this research is to help human fact-checkers speeding up the work. Fact-checkers have played an essential role for fighting against misinformation, which has created many problems of the world. However, due to the large amount of messages posted on various websites and social media platforms, it is infeasible to check every piece of news or post. In this case, using machines to help human fact-checkers is inevitable, but fact-checkers are skeptical towards the automation of fact-checking because it lacks a proper explanation. Nevertheless, we see a silver lining, that is, although there are a massive number of messages, many of them are similar or even duplicates. Here, let's see an example of some repetitive messages from Twitter after some pre-processing of the tweets. The 5 posts are all talking about that taking a flu shot can cause a false positive for the COVID-19 test. In fact, there are many more tweets like this conveys the same idea of the claim. In this study, we want to exploit this observation and propose a two-step pipeline to fill the gap between human fact-checking and machine fact-checking. Suppose we have our data from Twitter. The idea of this pipeline is to first cluster those tweets so that each group contains only semantically similar ones, and then from each cluster, we want to come up with a summarized version of the tweets that can represent the whole group. To implement this pipeline, we have some challenges, mainly due to the unsupervised nature of this task. First, for clustering, we need to group similar sentences together. However, it is hard to capture semantics of a given sentence. For example, we can convey the exact same idea with very different words. Second, we do not know the final number of clusters our method should find, and because of the large number of original messages, this unknown number of clusters will be large. Lastly, as this is the first work proposing this pipeline, we lack of annotated datasets for evaluation of the performance. Now, we introduce our message grouping. As we have mentioned, this phase is to group messages related to the same claim together. First, we need to embed sentences so that semantically similar ones are close in the embedding space. For this, we choose to use the library sentence transformers, which provides state-of-the-art pre-trained transformer models for sentence embedding. Then we construct a similarity matrix for every pair of sentence embeddings. We choose cosine similarity as the similarity measure. For the actual clustering, we adopt two types of clustering. First one is distance-based agglomerative clustering, which starts from every single message as a cluster and then merge two clusters if their distance is smaller than the threshold. In our case, we will merge them if their similarity is larger than the threshold. The second grouping method, we adopt Leiden community detection, which is a graph-based clustering. This method aims to optimize the modularity of the graph by moving and merging nodes into different communities until finding the division that reaches the maximum modularity value. And this process is repeated until we find a stable maximum modularity value. Both clustering methods need a similarity threshold, and we set them to be the same for both. Now we introduce our short message summarization. For summarization, we aim to extract a representative claim from each cluster. We first propose a graph-based extractive summarization. For this, we first construct a e-neighborhood graph for each cluster, and then we measure the representativeness of each node by calculating their centrality measures. Two types of centrality measures are used here. The degree centrality measure is based on the degree of each node. So the one with the most links has the highest degree centrality. For multi-centrality index, multiple measures are taken into consideration: degree, page rank, and betweenness. In addition, we also utilize tweet metadata that is the number of retweets and number of favorites, to calculate this number. After assigning the weight to each node, we will select the one with the highest to be the representative as the group. And we also remove some clusters with only a few nodes. And we adopted also another type of summarization method based on transformer models. This model is an extractive model that takes some input and generates a short summarization. An intuitive way to do this is to concatenate all the messages together and fed into a summarization model. However, we cannot do this directly because the model has limited input length. To solve this issue, we remove duplicates and new duplicates from each cluster. And then after this, the number of clusters, number of messages in each cluster are largely reduced. Then we could concatenate the remaining tweets in the same cluster as input to generate a summary. We utilize two types of models, BART and T5, for comparison. Now we present our experiments. First of all, for the dataset, we intend to have one that has ground truth summaries. The COVID is suitable for this purpose because the way the tweets were collected. For each news article, tweets that mentioned this news URL were being collected. And as each news piece has a claim summarizing the news content, we can treat it as a ground truth for our short message summary. After downloading the dataset, we need to perform some pre-processing. First, we remove the duplicate tweets with the same ID and also those tweets less than 5 words. And we also need to remove some tweets that are not relevant to the news claim. An example is shown on the right, in which the tweet content is totally unrelated with the news claim. So we have to remove cases like this to be able to use the news summary as some ground truth for tweet summaries. After this, we have around 29K messages remaining in English associated with around 1,000 news articles. So now we show some results of the clustering results with respect to the different similarity threshold. Since we do not have ground truth label for clustering, we use silhouette coefficient as the evaluation matrix, for which with higher value indicating a better defined cluster with less overlapping among clusters, except for the agglomerative and latent clustering. We also consider the original tweets that cluster separated by the news. From the graph, we can see that silhouette coefficient increases with the similarity threshold. When the threshold is closer to 1, agglomerative and latent, the results are similar. This is because when the threshold is high, they are only grouping near duplicate tweets together. And comparing them both with the news, their value is a lot higher than the news summaries originally providing a data set, which means our method is actually performs better than the original separation. And for the selection of the similarity threshold, we consider to select the one that is not as high as possible, because we want to make a balance of keeping more clusters and also including semantically similar posts that are not overlapping in words. To further compare the clustering with original clusters separated by news, we list the news summaries that are in one cluster. In this cluster, tweets associated with 3 news pieces are together. We can see that the news claims are actually similar, which indicates that our clustering is indeed performing better than the original separation. We now show the results for the whole pipeline, combining clustering and summarization. The evaluation matrix are ROC score, which evaluates the word overlaps, and the word score, which measures the semantic similarity, and the Average summary length, the measures indicates the informativeness of the summaries. From this table, we can see that extractive summaries, the DG and MC outperforms the abstractive summarization about 95, except for the average summary length. This is because most tweets are repetitions of the news claim, and extractive summaries, they select the one of the tweets to be the summary that can be more similar with the news claim. On the other hand, abstract models combine multiple different tweet content, so the summary are usually longer and they overlap less with the news summaries. Comparing the two clustering methods, the agglomerative and Leiden, they actually performs quite similar, but we consider Leiden to be better than agglomerative because that it has around 100 less clusters than agglomerative, and without losing much performance in terms of the matrix what we use. And overall, this fully graph-based pipeline with Leiden and the extractive summaries performs the best among all combination of methods. To have a more qualitative evaluation of the extractive summaries, we also invited a human fact-checker expert to access the result. The task is to evaluate how well a given summary represents its associated tweets by giving a score from 1 to 5. We randomly select 50 samples for each summarization method and calculate the average score for each one of them. The human evaluation results show that the 4 methods all achieved high scores, with extractive methods slightly higher than abstract ones. Here we present an example of the final results, and here are the tweets in the same cluster. You can see that these 4 tweets, they are indeed similar, related to the claim that is taking more alkaline food above the coronavirus pH level, which varies from 5.5 to 8.5, can help killing the virus. And here are some more examples in this cluster that also is related to this same claim. This example indicates that our clustering performs reasonably well. Continuing this example, we now show different versions of summaries for the tweets. The first one is the ground truth news summary. The second one and third one are the graph-based extractive summaries. In this case, the two methods select the same tweet as a summary. The last two are the transformer-based abstractive summaries. Both methods also covers the main claim. Comparing with the TG and MCI, they overlap less with the news summaries, confirming our previous findings. In conclusion, in this work, we proposed a new pipeline for more scalable fact-checking by grouping and extracting information from a large amount of social media messages. We also proposed an entirely graph-based approach for the pipeline with Leiden community detection and extractive summarization that utilizes tweet metadata. The results showed that the graph-based method had the best performance. In addition, our pipeline reduces original around 29K tweets to around only 700 claims, which can show the potential of our work to scale up the fact-checking process. For future work, we plan to apply the pipeline to bigger datasets of millions of short messages to address the importance of clustering and summarization efficiency. We also plan to further reduce the number of summaries, as we have observed that some extracted summaries are borne out claims and not useful for checking. We intend to do this through a claim detection. In addition, our pipeline is fully unsupervised, and we lack of a dataset for better evaluation of the clustering results. But in the future, we would like to develop a standard dataset for the evaluation. Thank you very much for your attention. Our data and code are available through the link on the slides. Feel free to check out.